Hello friends. So today we are going to discuss few questions, and these questions are from the year 1999, and from the year 99 there are two questions, and the other questions which are from the year 2000, and these are total in 4 in numbers. So total we are going to discuss today 6 questions. So in the first one, which is from year 1999, and it states that a charged particle is released from rest in the region of steady uniform electric and magnetic fields which are parallel to each other. The particle will move in a, so we have to find out the locus in which the particle is going to move. So here the one important thing is that the particle initially is at rest, and later on it moves in the region where both electric field and magnetic field are parallel to each other. So for the sake of convenience, we assume that electric field and magnetic field they both are along z axis. So let us assume that. And initially the particle is at rest. So you can see from initial condition we have the particle is at rest. Particle is at rest. So under this condition we can say that its velocity is equal to 0. So therefore the magnetic force which is suppose is Fm given as Q V cross B, this product this will be equal to 0 because the velocity is 0. And now we come to our electric force. Electric force is suppose given as Fe, that will equal to Q and multiply by E. So at this position, initial condition, only the force which will be acting on the particle will be the electric force. Okay. And this will accelerate the particle along the direction of E, along the direction of electric field, that is Z axis. And when it gains some velocity, so we can see from there that velocity builds up in the direction of E, and this electric field is in parallel with the magnetic field. So the velocity is also in z direction, magnetic field is also in z direction. we can say that velocity and magnetic field are parallel to each other. Therefore, our V cross B will be equal to 0. So from here we can draw important conclusion that the magnetic field never contributes to the motion of the charged particle. You can say that from here I can say my Fm is also still equal to 0. Therefore, magnetic field never contributes to the motion. So it means the only force that is contributing to the motion is our electric field, and because of this electric field the particle only moves in the straight line. Okay. You can say the charged particle moves in a straight line. Therefore, option number A is the correct option. Option A is correct. We come to the next question. It says that the region between x equals 0 and x equal L is filled with uniform steady magnetic field minus B naught k unit vector. A particle of mass m, positive charge q, and velocity v naught I unit vector travels along x-axis and enters the region of magnetic field. Neglect the gravity throughout the question. And based on this, we have two questions, and it says that first question, find the value of L if the particle emerges from the region of the magnetic field with its final velocity at an angle of 30 degree to the initial velocity. And second question is that find the final velocity of the particle and the time spent by it in the magnetic field if the magnetic field now expands to 2.1 multiplied by L. So in this case, we have, you can say, we have a region of magnetic field, and that region of magnetic field is between our 0 and L. So we can draw a rough approximate diagram for that, and in this diagram we can try to understand for the first case. So let us start with part A. And part A, it says that we have a particle. This is our x-axis. This is our x-axis and this is our y-axis. And the particle initially is trying to move along x-axis with the velocity of v naught. And we have magnetic field that is our in the direction of minus B naught k unit vector. So we can say our magnetic field is into the plane of the paper. And because of this magnetic field, and it is given this magnetic field is between our x is equal to 0 to x equal to L. So let us suppose this is our x equal to L and this is our x equal to 0. So this total distance comes equal to as L. And so because of this magnetic field, it will try to move in a like this a circular path. And we say that if C is the center of this circular path, if C is the center of circular path, and we have R is the radius of the circular path, and it is making an angle of theta with the vertical, and this is our velocity v0. Because of the magnetic field, it will try to move in along this, and we can say this is approximately equal to theta. So this is our, you can say, approximate diagram, and we can say that initial velocity is our v0. It is direction of v0 and I unit vector. We have the magnetic field, that is our B, and this is equal to minus of b0 k unit vector, and region of the magnetic field is from x is equal to 0 to x is equal to L. Region of magnetic field is from our x equal to 0 to x is equal to L. So these are the few things that are given to us. So first of all, let us find out what will be the magnetic force acting on this charged particle. Magnetic force, let us call that as Fm, which will be given as Q B cross B, and we substitute the respective values. We can write this as our Fm is equal to our Q, and here we have V0 I unit vector, and this comes cross product minus B0 K unit vector, and we can write this as minus Q V0 B, and here comes as I cross K, and that will be nothing but minus of J, and minus of minus gives us plus, so this comes as plus Q V0 B0 and J. Okay, so the figure we can also see that our particle tries to move along the y-axis. Okay, we can say this is nothing but V0 J unit vector, and so we can say that our particle moves upward in plus y direction. So therefore it traces, or we can say it makes a circular arc in the xy plane. So we can say it makes a circular arc in the xy plane and counterclockwise. So therefore we can find out the radius of this circular arc. So we get radius of circular arc is equal to r, and that is equal to m v naught divided by q b naught, and it is given the angle between if the particle emerges from region with its final velocity at angle of 30 to its initial velocity. So the angle between the initial and final is given as 30 degree. We can say that angle between initial and final velocity, that is our theta, is equal to 30 degree. And so we can call this distance also L. So here we can use sine of theta, and we can find out that sine of theta is equal to L upon R. So this gives us that our L upon R is equal to, theta is 30, so this comes as sine of 30, and which is equal to 1 by 2. So we can say from here that our L is equal to R by 2. So if we simply substitute, you can say formula for R, we get this as of L will be equal to m v naught divided by q times b naught. And from this L is equal to R by 2, so it basically means that the particle will be moving out of the magnetic field also. We can draw that our L, the length of the magnetic field with respect to the radius, is our 1 by 2. Now we come to the second part, part B. And in part B, it says that the magnetic field now is extended to a different region. Extended, simple. So you can say the magnetic field is extended, and the upper limit, upper value, suppose is called as L prime, then this L prime will be equal to 2.1 times L. We substitute the value of L, we get this as 2.1 multiplied by R by 2, and this comes as 1.05 times R. So it means the particle is going to travel with the arc length of 1.05 times R. You can say from here the particle travels arc length is equal to 1.05 times R inside the magnetic field. Inside the magnetic field. So once again we can draw an approximate diagram for that. And so with this is our x-axis and we have our y-axis, and the particle, now we have a L prime. So let us suppose this is our L prime, and L prime is our 2.1 times L, and the arc, obviously because of the magnetic field, the direction is same, so it is going to traverse, making a something like this. In this direction. Okay, initially it is in V naught, so it will try to go into a semicircular portion. So let us find out the how much angle will be making with the, you can say, as it is going to traverse in this xy plane. So let us say that when the particle moves in a circular path, the arc length let us suppose that is given as S, radius capital R, and angle of theta, and angle theta, and this theta is in radians. So we can write the relationship between them, that our S is equal to R multiplied by theta. So from here we can say our theta is equal to S upon R. Please keep in mind this is in radians. And for, you can say, S we already know is our the total arc length, and that will be our 1.05 times R. So we can say S is equal to 1.05 times R. So this comes as theta is equal to 1.05 times R divided by R. So this comes as 1.05 radians. We can easily convert this into degree. So we can say our theta in degree will be equal to 1.05 multiplied by 180 and divided by pi. And this comes approximately equal to 189 degree. So you can say, for the sake of convenience, we can just assume that this is approximately equal to 180 degree. So it means the final velocity is now completely reversed, because now the total angle traversed by the, or we can say made by the final velocity is 180 degree. So you can say at theta 180 degree, final velocity is completely reversed. Reversed means in direction only. So you can say V final will be equal to minus V naught times I. Okay, and this is our here V final. This is our V final. Okay, magnitude is going to remain same, but the only thing that is going to change is our direction. Okay, so that's why it comes as minus V naught into I. And now next is quite simple. We have to find out the time spent in the field. So you can say time spent in field. So you can say for full circle of radius r, time is given as 2 pi r divided by V naught. We substitute the value, we get this time is equal to 2 pi m, and we get this as q V naught. And this is, let me write it, time for full circle. Time for full circle. But the angle traversed by the particle is only 180 degree, that is the half of the full circle. You can say since 180 degree corresponds to corresponds to half the circle. Therefore, time spent is small t, half of the full circle. This comes as pi upon pi m multiplied by q b naught. So this was our thing asked. Yeah. Find the final velocity and the time spent. Now we come to the next question. In this, it says that it was asked in the year 2000, and it says that an ionized gas contains both positive and negative ions. If it is subjected to simultaneously to an electric field along plus x-axis and a magnetic field along plus z direction, then we have to find out in which direction the ions will be reflected. Okay. So therefore, we are given that we have electric field and that is given in plus x direction, and then we have magnetic field that is in plus z direction. And we have, I think, both positive and negative ions. Okay, so let us start with for positive ions. You can say positive ions, the electric field that is of E, and this is our in plus in I direction. Therefore, and the positive ion, because of the electric field, they accelerate in positive x direction. And we can write also that the velocity with velocity that will be over positive v in x direction. Now we come to the magnetic field. Magnetic field that is over B, it is in plus z direction, and because of this we can find out the force. Magnetic force that is a F, let us write it as positive because of the positive ion, and this will be coming as Q V positive and cross B. We substitute the respective, we can say, we are only interested in direction, so we can directly substitute their unit vectors. So we have I unit vector, and here we have K unit vector. So this gives us minus J unit vector. Okay. We are only interested in the directions. So it means minus J, so which basically means in minus Y direction. Now we come to the negative ions. And for negative ions, the electric field this will be giving us our E, and that will equal to once again in plus I direction. Okay, and you can say accelerate it in minus I direction. So accelerate in minus x direction with their velocity will be equal to minus v and I. Now we can find out our magnetic field. Magnetic field is our B, and this is plus in k direction. So magnetic force that is Fm negative will be our minus of Q, and this comes as, let us me write this as negative. So this comes as V negative cross B. And once again, we are only interested in the, you can say its magnitudes. So we can rewrite this as minus, and here comes it as minus of I cross K, and this gives us that the force, because of magnetic field, will be our minus J unit vector, and this once again means along negative y direction. So it means both are deflected in negative y direction. So if we check the option number C is the correct option. All ions are in minus y direction. Option C is correct. Next question. It says that an infinitely long conductor PQR is bent to form a right angle as shown in figure. A current I flows through PQR. The magnetic field due to this current at a point M is given as H1. Now, another infinitely long straight conductor QS is connected at Q, so that the current I by 2 is in QR as well as in QS. The current in the PQ remains unchanged. The magnetic field at M is now given as S2. The ratio of H1 and S2 is. So we are given a figure, and in this figure we have a straight conductor which is bent in the form of L shape. So this is our conductor, and it is carrying current I. Okay. And in the first case, we have to find out that the magnetic field in first case at point M is given as H1. Later on, another conductor is connected to point Q. So this is another conductor connected to point Q, such that now the current in QR as well as QS is 1 by 2. Okay. So in the second case, the current becomes 1 by 2 here in this direction, and here also it becomes, sorry, not 1 by 2 but I by 2 and I by 2. The current in PQ remains the same. So this is the basic scenario. So we can divide this entire discussion into two cases. So we start with case 1. So in case 1, only PQR is there. Only PQR. And current is I. Okay. So we can draw the figure. Now this is only our PQR. So we have P, this is our Q, and this is R, and we have to find out the magnetic field at point M. Current here is given as I, and this is also for I. So we can draw the, let us suppose this is our x-axis and this is our y-axis. Therefore, we can say that current in PQ along positive x is our I, and current in QR, it is along minus y, and magnitude is same. And point M, this point M lies on positive y axis, or we can say extension of QR at extension of QR. So let us find out the field because of the two components or two state current carrying wires. One is our PQ, another one is QR. So we say magnetic field contribution. Magnetic field contribution. First is due to PQ, and the PQ is nothing but our semi-infinite wire. Okay. So PQ is our semi-infinite wire. Therefore, the magnetic field, that is B, because of PQ, is equal to mu naught I upon 2 pi A. And for sake of convenience, we assume that this distance is our A. This is our A. Now we can find out due to QR, and the point M, like I said, lies on the extension of QR. M lies on extension of QR. Therefore, magnetic field due to QR is equal to 0. So total field due to this case 1, total magnetic field for case 1, which is given as H1, is our magnetic field due to PQ plus magnetic field due to QR. We substitute the respective equations. We get H1 is equal to mu naught I upon 2 pi A plus 0, and this comes as mu naught I upon 2 pi a. Now we come to the case 2, where we have an extra wire connected to Q. We have case 2, which is a combination of our PQR plus QS, and in this case current splits. So we can draw the approximate figure for that also. So we have PQR, and now we have a QS. Current in PQ is still our I, and current in QR is now I by 2, as well as in QS is our I by 2. And this is point M, which is at a distance of A. So we can say PQ, it carries a current of I positive X direction. Then we have QR, which carries a current of I by 2, and its direction is negative Y direction. And we have QS, which also carries a current of I by 2, and direction is plus X. So now we find out the respective magnetic fields of all these three sections. So we say magnetic field contribution. Magnetic field contribution. So first is because of PQ. So we can say magnetic field because of PQ is equal to mu naught I upon 2 pi a. Its direction is out of the plane. And then we have our second, and second is due to QR, and QR, like in first case, the magnetic field due to QR will be equal to 0, because it doesn't change anything. Although the current becomes half, but the point M is still lying on its extension. And we come into third part, that is due to QS, and we have B QS is equal to mu naught, current becomes half, and this becomes 2 pi a, and which is our mu naught I upon 4 pi a, and the direction is out of the plane. Out of plane. So we can find out the net magnetic field. Total magnetic field in case 2, and which is given as our H2. H2 will be equal to magnetic field due to PQ plus magnetic field due to QR plus magnetic field due to QS. So this comes as mu naught I upon 2 pi a plus 0, and we have mu naught I upon 4 pi a. This comes as 3 by 4, mu naught I upon pi a, and we have to find out the ratio. So we can say our h1 upon h2. So we substitute the value, we get this as 3 by 4 mu naught I upon pi a, and here we get 1 by 2 mu naught I upon pi a. These terms cancels out, and this gives us 1 by 2, 3 by 4, which finally gives us 2 by 3. So the ratio of H1 and H2 is 2 by 3. So the option number C is the correct one. Option C is correct. Now we move to the next question. In this case, it states that it was asked in the year 2000, and it gives that a particle of charge q and mass m moves in circular orbit of radius r with angular speed omega. The ratio of the magnitude of its magnetic moment to that of its angular momentum depends on. Basically, we are going to find out the ratio of magnetic moment, that is our mu, angular momentum, that is our L. So we have to find out mu upon L and its formula. So we know the standard formula for magnetic moment is current and multiply by area. So we say magnetic moment mu is equal to I into A. A is the area of the loop, and in this case it is our pi r, so small r, pi r square. And so we can write that our mu is equal to current multiplied by pi r square. Now we have to find out the value of the current, and for current we are first of all going to find out the charge, and we are going to find out for charge with respect to time. That will be giving us a current. So we say that current due to orbiting charge, current due to orbiting charge, and we can write the time period for one full cycle, the time period for one full cycle, that is our t, will be equal to 2 pi upon omega. And from here we can say our current, that is I, is equal to q upon t, and this gives us a q omega divided by 2 pi. Therefore magnetic moment, that is our mu, it comes as q omega 2 pi multiplied by pi r square. Pi and pi goes away, and we are left with q omega r square divided by 2. This is the equation for the magnetic moment. Now we can find out the angular momentum. Angular momentum, that is of L, and this L we can write is equal to our mv multiplied by r, and v we already know is omega r. V is equal to omega times r. So we substitute it, we get our L is equal to m omega r multiplied by r. This gives us m omega r square. Now we find out the ratio. We want this as magnetic moment to angular momentum. We get magnetic is 2 omega q omega r square divided by 2, and this whole divided by m omega r square. So here r square omega cancels out, and this comes as q upon 2m. So the ratio, it is dependent upon q and it is dependent upon m. So the option is option number C is the correct option. Option C is correct. Now we come to the next question. It was asked in the year 2000, and it says that a circular loop of radius r is bent along a diameter and given a shape shown in figure. One of the semicircles K and M lies in xz plane and other lies in KLM in the YZ plane with the centers at the origin. Current I is flowing through each of the semicircle as shown in figure. So based on this description, we have two questions. First states that a particle of charge q is released at the origin with the velocity minus v naught I. Find the instantaneous force F on the particle. Assume the space is gravity free. In the B, it says that if an external uniform magnetic field B naught J is applied, determine the force F1 and F2 on the semicircles KLM and K and M due to the field, and the net force F on the loop. So we are given the figure, and in this figure we have two wires. One wire is our KLM and another wire is our KNM, and the current that is flowing through the respective wires is I. Okay, and the direction is also given to them. In this case, first of all, we are going to find out if the charge q is released at the origin. So this is our origin, and charge q is released. We have to find out the instantaneous force F on the particle. So we start with part A. In part A, because it is a semicircle, so we can say the magnetic field at the origin. At the origin, or we can say magnetic field at the center of the loop. At the center of the semicircular loop. Semicircular loop, we can write the formula, that is our B semicircle is equal to mu naught I upon 4r, and here we have a n unit vector. Okay. And now we have two loops, so we can just make an analysis of this magnetic field Bs according to two loops. Okay. So first we have that KLM lies in the YZ plane and current flows from K to L and to M, K to L and that to M. Okay. So we can say, based on the direction of flow of the current, we can find out the direction of magnetic field at the center, which is our origin. Therefore, we can say that field at the origin, and this origin is nothing but center of semicircle. Center of semicircle, field at the origin is along positive direction. Therefore, let us call this as B1 is equal to mu naught I upon 4R, and here we have a I unit vector. And similarly, we can do for K and M. Second, we can say that our K and M lies in our XZ plane, and current flows from K to N and to M. Therefore, magnetic field at the origin is along positive J. So magnetic field in second case, let us suppose that B2 is our mu naught I for R J unit vector. So now we can find out the net magnetic field. Net magnetic field at origin which is B, and that's value equal to B1 plus B2. So this comes mu naught I upon 4R, and we have I plus J. Okay. Next we have to find out, okay, basically we are interested in force. So we've got the magnetic field. Now we can easily find out the force. So we say force on the particle. Force on the particle, and the velocity is given as minus V naught I unit vector. So the force, let us suppose, is given as our FB, that will be equal to Q V cross B. We substitute the respective, we get minus V naught I cross, and our B is mu naught I upon 4 times R, and we have I plus J. And now it is simple calculation of the cross product. So we can say that we get this, the magnetic field will be equal to minus q v naught, and here we have mu naught I upon 4r times k unit vector. So this is our the force which was asked in the part A. Now we come to the part B. Now in part B we have external magnetic field. External magnetic field, and that is our B naught, given as B naught in J direction, we can say in Y direction. And we know that the force on a current carrying wire or conductor in the magnetic field is our I, and we have dl cross B. We say that force on a current carrying wire in a magnetic field that is given as F current, and we have dl cross B. Total we need to find out, which you can just integrate it, and we can make analysis for each semicircle. We start with force on KLM, and this lies in our YZ plane. Magnetic field, that is external magnetic field, that is our B naught, is given as B naught in Y direction, and this dl element, we have to remember that this dl element is a tangent to the loop. The tangent, because it is tangent to the loop, and as the semicircle is in YZ plane, it's always perpendicular to I unit vector, that is our x direction. So we can say the net force on the semicircular arc let us suppose that is given as F1, and that will be equal to I, and we have chord vector and cross B. And for KLM circle, we can just write the chord vector. You can say for KLM, the chord vector is from K to M, which lies along I. which lies along I. Therefore, we can say length will be equal to 2r, and in the vector notation we can write this as 2r and our I unit vector. Now we can find out the force. We can say F1 will be equal to current, and we have here 2RI cross magnetic field is our B0 times J. So we can just easily solve it now. It becomes 2RBI, and we have I cross J, and which will be equal to K. So we can say our F1 will be equal to 2I RB, and we have a K unit vector. Similarly, we can find out the force on K and M, which is in XZ plane. Force on K and M, and which is our XZ plane. And here also the chord goes from K to M, and it will be also along I. Therefore, we can say that chord goes from K to M, and also we have it is 2R I unit vector. Magnetic field is same, so the force F2 can be written as current is also same. We get this as 2RI cross B0J, and this once again comes as 2IR B0 K unit vector. Net force will be the algebraic sum. So we have net force over F will be equal to F1 plus F2, and in both the cases it is same, so we can just write it as 2 times 2I R B0 K unit vector, and this gives us a 4I R B0 K unit vector. So this is our net force on the loop. Yeah, so we found out F1, F2 as well as net force on the loop in the external magnetic field. And I think this was the last question. Yeah. So this completes the questions which was asked in the year. 2 questions from 1999, and we had 4 questions from 2000. Okay. So let me first check. We have 1, 2, 3, 4, 5, 6. So this completes all the 6 questions. Thank you.